Alright class, today we are going to talk about the diesel cycle, ideal cycle for compression ignition engine. So in this chapter 9 we talked about, in the first class we talked about um, the gas power cycle, and then we also talked about the Otto cycle and ideal Carnot cycle, right? So today we are going to talk about the diesel cycle. Here I choose some picture for demonstration purpose of the diesel engine, from the latest Ford 2020 Super Duty vehicle. uh, they use the V8 turbo diesel engine, right? So I mean, to understand this diesel engine, we need to understand that ideal cycle. What is the ideal cycle of the diesel engine, and what is the working principle of diesel engine? So when we are comparing this diesel engine or the compression ignition engine with the Otto cycle or spark ignition engine, the difference is basically that, in gasoline engine or Otto cycle, basically there is a spark plug, right? Or gasoline engine, there is a spark plug that is initiating the combustion of the air fuel mixture, right? However, in the compression ignition engine or diesel engine, what is happening is that when the fuel is compressed, right, when the fuel is compressed, it generates, like, due to the compression, it's generates the temperature, right? It gets heated up. As soon as the air is coming within that chamber, it's uh, it's starting the combustion. So there is no need of spark plug in the diesel engine or compression ignition engine, right? So diesel engine, or we can name it as a compression ignition engine as well. Compression ignition, right? So now we know the difference between the compression ignition and spark ignition. So this is spark ignition, and the diesel engine is basically the compression ignition. So we know the difference between. So in the previous class we talked about the spark ignition cycle, right? Ideal cycle. Now today we're going to talk about the compression ignition cycle. So let's go ahead and draw the PB diagram and TS diagram of the ideal diesel cycle, right? Ideal diesel cycle. So ideal diesel cycle, first proposed by Rudolf Diesel. Actually, I would write it this way, right? Rudolf Diesel in 1890. So year of 1890, he proposed the first ideal diesel cycle. So the PB diagram of that ideal diesel cycle, it's gonna look like this is P and this is V, right? So PV diagram, it's basically from 1 to 2, it's compression, and then here, and then so this is 1, 2, 3, 4, right? And this cycle is going like this way. And then TS diagram, it's basically 1 to 2 is isentropic, and then constant pressure, and then isentropic again, and then constant volume. So this is 1, 2, 3, 4. Basically the heat addition or heat rejection is happening at constant pressure, heat addition, and constant volume, heat rejection, right? Similarly, we can write it here, heat addition and heat rejection. So these are the ideal cycle of the ideal diesel cycle, right? So PV diagram and TS diagram. So now if we write the energy balance equation, right, for this ideal diesel cycle, then for process 2 to 3, um, process 2 to 3, basically this one, it's the constant pressure heat addition, constant pressure heat addition, right? Excuse me. So for this process we know that Q in minus WB out, which is equals to change in internal energy, U2 minus U3 minus U2, right? So from here we can write Q in equals to P2 at this one, temperature pressure is same, P2 equals to P3, so P2, which is and then V3 minus V2, right, plus U3 minus U2. So in terms of enthalpy we can write this equation, which is H3 minus H2, and in terms of constant pressure, since this process is happening at constant pressure, this line, right, constant pressure, so Cp times T3 minus T2, right? So this is the Q in. And process 4 to 1, if we look at the process 4 to 1 right here, it's basically constant volume heat rejection, constant volume heat rejection. So what is happening here, heat rejection means that negative Q out, right, equals to U1 minus U4. So basically we can write Q out equals to U4 minus U1, right, which is CV times T4 minus T1, because it's constant volume, heat rejection is happening at constant volume. So now we know the Q in and Q out, right? So by the definition of efficiency, so we know that diesel cycle efficiency, eta thermal of diesel, diesel, which is equals to net work output divided by net heat input, right, which is work output is nothing but how much energy is utilizing, right, input minus Q output divided by Q in. So it will be 1 minus Q output over Q in. So we know all of those. So 1 minus Q out we just derived here, Cv times T4 minus T1, Cv times T4 minus T1, and Q in Cp of T3 minus T3 minus T2, T3 minus T2, right, at a thermal efficiency of the diesel engine. Now we can rewrite this expression just by taking out this T1 from that expression, and we also know that Cv divided by Cp equals to the specific heat ratio, which is the case Cp divided by Cv, right? So we can write it in this way, T4 minus T1 divided by T3 minus T2 times K, right, since K equals to Cp over Cv. Okay, now let's do this. Eta thermal equals to 1 minus T1, take out the T1 outside the bracket, so T4 divided by T1 minus 1, and here let's do T2, T3 divided by T2 minus 1, right? So if we do this, then we are going to define the T1 versus T1 divided by T2 a new term, or T4 divided by T4 new term. Before that, let's define another definition, the cut-off ratio. Cut-off ratio, which we write it RC, is nothing but the ratio of the cylinder volume before and after the combustion process. So volume of the cylinder after combustion and volume of the cylinder before combustion, right? So that means if we take a look right here, what is happening when is the combustion process is happening? Before combustion the volume is V2, and after the combustion volume is V3, right? So that means it will gonna be RC equals to V3 divided by V2. So this is the definition of the cutoff ratio. If we write it in unit mass, then it will be V3 divided by V2, right? So we know that. Now this process, let's take a look in 1 to 2 process. What is happening in 1 to 2 process? So this is an isentropic process. We can clearly see that entropy is same for the process 1, and similarly for process 3 to 4 it's also isentropic process, and it's an ideal case, and everything is happening here, right here. It's in the closed system, right? So this is a closed system, so nothing is crossing the boundary. The mass is not crossing the boundary in this case. So it's a closed system, and also it's a isentropic system and ideal gas. So now from the ideal gas and isentropic condition relation, we can write all those relationship between the temperature versus volume, right? So for process 1 to 2, right, we can write that T2 divided by T1 equals to V1 divided by V2 to the power k minus 1. So we know this relationship, right? However, if we write it in terms of T2, then it will become T1 times R of k minus 1, right? So R is nothing but the compression ratio. Excuse me, let me add some pages here. So R equals to compression ratio, which we discussed about the last class, which is V1 divided by V2 or V4 divided by V2, right? So, excuse me, V2. So we know the temperature T2, right, in terms of T1, and for process 2 to 3, right, when the pressure is constant, we know that the relationship becomes T3 divided by T2 equals to V3 divided by V2, right? And then V3 divided by V2 we just defined as a cutoff ratio RC, which is equals to, actually this is equals to RC, right? And so in terms of T2, T3 will become T2 times RC, right? So we know T2 and we know that T3. Now let's derive the T4. So for process 3 to 4, right, which is isentropic, then we know that relationship T4 divided by T3, which is equals to V3 divided by V4 equals to K minus 1. So if we simplify this one in terms of RC, which will become T4 equals to T3 times V4 divided by V3. I'm rearranging it, right? Then it will become 1 minus K, and then T4 equals to T3 times V4 over V2, V2 divided by V3. Basically this V2 and V2 will be omitted, and it will leave only V4 divided by V3, right? So we know this V2 over V3 is nothing but the RC. So if we write it in terms of compression ratio and cutoff ratio, it will become T3 times R over RC, which is equals to 1 minus K, right? So now we got the relationship of the T2. We just derived the equation for T3, so let's plug in that value, right? So T4 equals to T3 equals to RC times T1, right? And it will become R to the power K minus 1 times R over RC equals to 1 minus K. So now it will become RC T4 equals to RC to the power K times T1, right? So we got the T1, T2, T3 and T4. So now let's plug in all those value in the diesel engine. So the efficiency of the diesel engine will become, if we plug in all those values and simplify, 1 minus T1 times RC power K minus 1 divided by K times T2 RC minus 1, right? If we simplify this equation more, then it will become, actually I made a mistake here. So 1 minus this, right? So it will be 1 minus 1 over R to the power K minus 1 times RC to the power K minus 1 divided by K times RC minus 1, right? So from this equation we can see that if the compression ratio, or this term, right, this term, if this term is greater than, if this term is greater than 1, then what is going to happen is that efficiency of the diesel engine is going to be smaller, right? So the relationship for or we can write in this way, that if the compression ratio is goes up, and as well as the if the compression ratio goes up and the cutoff ratio goes down, right, then the efficiency of the diesel engine will goes up. So that's what we're looking at, this diesel engine efficiency. Anyway, so this is diesel engine efficiency expression. We'll use it to solve a math problem, right? Let's take a look on the so one more statement we can derive from this one. So if this term, right, RC power K minus 1 divided by K of RC minus 1, if this term is greater than 1, right, so if RC power K minus 1 divided by K times RC minus 1, if this term greater than 1, then eta thermal efficiency of Otto cycle is greater than the eta thermal efficiency of diesel cycle, right? and diesel cycle. So, and for diesel cycle, for diesel cycle or CI engine, compression ignition engine, typically the compression ratio value equals to 12 to 24, right? So yeah, so these are the this is the expression of the efficiency of the diesel engine. So let's talk one more term that we used in the last class: mean effective pressure. Mean effective pressure, which we call MEP, right? So we defined the MEP equals to the net work done divided by displacement, right? So net work done, we derived this one, which is equals to mcp of T3 minus T2 minus mcv actually mcv of T4 minus T1, which is, and the displacement is equals to V1 minus V2, right? W net output divided by V1 minus V2, right? We are writing in terms of the mass, mcp T3 minus T2. So this is the expression of mean effective pressure. But if we again simplify, or in terms of compression ratio and cutoff ratio, if we write this expression, then it will become P1 times the compression ratio of K times R to the power K minus 1 RC minus 1 and minus RC power K minus 1 divided by R minus 1 times K minus 1. So this is the expression for MEP that we're gonna use to solve the math problem if we have the compression ratio and cutoff ratio given for particular fuel. So let's go ahead and solve a problem based on the diesel cycle. So I choose this problem, exercise 9.46, which is the diesel cycle, air standard diesel cycle. It has the compression ratio is 16, right? So given solution, right, given the compression ratio basically R 16 and the cutoff ratio RC equals to 2. At the beginning of the compression process, air is at 90 kilopascal and 27 degree C. So if we write this, let me draw the diagram, PV diagram, so it will be easier. Okay, so 1 to 2 is like this, right? 1 2, and then 2 to 3 is this, and then here, and then it will become like this. Okay, 2, actually this is 3 and this is 4. So here heat in and 4 to 1 heat out, right? So this is V and this is P. So it's basically saying that during the process 1 to 2, the temperature is during that process 1 to 2, the temperature is 27 degree C, and the pressure is 95 kilopascal. Accounting for the variation of specific heat with the temperature, determine the temperature after the heat addition process and thermal efficiency, as well as the mean effective pressure. So let's go ahead and take a look for the process 1. So process 1 to 2. So this process 1 to 2, from the TS diagram we know that this is an isentropic process. However, the temperature is given here 27 degree Celsius, which is 300 Kelvin, right? And with respect to this um, temperature, if we look for the the internal energy, then we'll get it u internal energy u1 um, equals to 214.07 kilojoule per kg, and then ur1 equals to vr1 equals to 621.2. Basically I recorded all those properties from table A17, right? Marking table A17. And also I recorded the gas constant R, which is equals to 0.287 kilojoule per kg Kelvin, right? So for process 1 we know all of those information. Now from the relationship v1 divided by v2 equals to vr1 divided by vr2, we know that will become the vr2 equals to 1 over r, because this is the compression ratio, 1 over r times vr1, right? So basically it will become vr2 equals to 1 over 16 times 2 621.2. So we'll get vr2 equals to 38.825, right? So now using this this information vr2, right, using this information we can have the value of the temperature from the table, right? I recorded that one already, which is, let me write it, excuse me. Okay, the T2, which is equals to 862.4 Kelvin, and H2 equals to 890.9 kilojoule per kg, right? So I have those information right now. So for the, let's go ahead and determine the thermodynamic property or all those information for the process 2 to 3, right? So for process 2 to 3, we know that the relationship P3 divided by V3 divided by T3, which is equals to P2 V2 and T2, right? So here T3 is equals to V3 times T2 divided by V2, right? So P3 and P2 is, let me show you here, P3 and P2 is the same, right? So that's why we are using only, so they're omitted, so P3 and P2, they're the same. So basically it will become RC times of T2, right? So we know that RC value is 2 compression ratio times, we just determine the T2, which is 862.4. so we get the T2 value 1724.8 Kelvin. So this is the temperature they're asking for, right? But we this is the temperature, right? So based on this temperature, if we go to the from table A17 again, then by doing the interpolation based on this T through, we can get the enthalpy, which is 1920 10.6 kilojoule per kg, and we have Part-3 specific volume, which is 3 equals to 4.546, right? We have this information. So now in the problem, so basically we determine this one, number A, and then the B is asking that what is the thermal efficiency. So we know that we know the thermal efficiency, the definition, but before that we need to determine that heat addition, right? Or what is the heat input in that diesel cycle. We don't have this information, so let's write the heat addition Q in equals to H3 minus H2. So H3 we determined just right here 1910.6, and H2 we got it here 890.9, 890.9. So we know that heat addition to that system, it's basically 1019.7 kilojoule per kg. So this is the heat addition, right? So for process 3 to 4, this is a isentropic expansion, right? Process 3 to 4, basically we know the relationship VR4 divided by VR3 equals to V4 divided by V3, right? So basically for this one, VR4 equals to V4 divided by V3 VR3. So we know all this information. Basically in V4 divided by V3, we know that this is so here it will become, if we write the V3 in terms of V2, then it will become V4 divided by 2 times V2, right, times VR3. So V4 and V2, it's basically the compression ratio. So VR4 equals to compression ratio, we know R over 2 times VR3. So let's plug in all those values. VR4, R we know that 16 over 2, and VR3 we got it 4.546, right? So VR4 is basically 36.37. Again, with respect to this value, if we go to the table, then we can get the enthalpy at 4, which is equals to internal energy at 4, which is equals to 659.7 kilojoule per kg, right? So now we have this information U4. Now we can determine that what is the Q out, right? So for process 4 to 1, where the heat rejection is happening, right, and it is a constant volume process, right? So Q out is equals to U4 minus U1. We have all this information, which is 659.7 minus 214.07 Q out. So Q out will become 445.63 kilojoule per kg, right? So now we have the Q in and Q out. So the eta thermal efficiency of the diesel cycle, it's basically 1 minus Q out over Q in, right? So it will become eta thermal of diesel equals to 1 minus Q out 445.63 over 1019.7, so which is 56.9, 3% efficiency. Right, so this is another answer. So now the third thing they're asking is that mean effective pressure, right? So MEP, we know that MEP definition is that W net output, right, divided by maximum displacement, which is equals to V1 minus V2. We just derived this expression. So the W net output is basically that Q in minus Q out, which if we plug in all those values, then it will become 574.07 kilojoule per kg, right? And from this for the state 1, from universal PVT relationship, we can write that P1 V1 equals to R T1, right? So from here we can determine that what is the volume, R times T1 over P1. So we have all of those value. If we plug in that 0.287 times T1, we got 300 Kelvin, divided by P1, we initially had 95 kPa, right? So we have this V1 equals to 0.906 meter cube over kg, right? So this is the maximum volume. So from the compression ratio, we know that V1 over V2, right? So V2 will become P2 will become V1 over R. So we have V1 value just got 0.906, and R we have it's 16, right? So it will become 0.056625. So now we have all of those information, right? So let's just plug in MEP expression, which is equals to 574.07, right, network output divided by the change in the volume. So maximum displacement 0.906 minus 0.056625. so the MEP will become 675.87 kilo Pascal. So that's the expression for MEP, or that the answer for MEP. So that's all about this problem, asking for the diesel cycle, ideal diesel cycle, right? So we determine the temperature, we determine the thermal efficiency, and we also determine the mean effective pressure. So that's all about this class, and I'll come back with the another cycle, and we will also do the same. We'll do the derivation first, or we'll talk about the theory first, and then we'll go ahead and solve the problem. Thanks for watching this video.